Right. Okay, great. So we're going to move on to...
Ma'am, what year paper is this?
It's, I think it's 2017. Let's just check. Yeah, 2017.
Thank you, ma'am.
I'm going to make it a little bit smaller so that it fits better so we can see the questions, because I think that's big enough. Yeah, that's fine, right? You can all see it. Is that okay? All right.
Yes, ma'am, on my side.
Okay, super. All right, so you're having a look. Always read the instructions first, okay? They're telling you that O is the center. Whenever they tell you that O is the center, you make sure that you fill in everything there is to know about the center and what it tells you, okay? So what does the center tell you? It tells you to look for radii, for example. So always fill that in first, because why? Why do we always fill that in? Because it might form simultaneous equations, okay? So we always make sure we do that. All right, so that equals that. So that's your radii. And then you're looking for all the theorems that involve a radius, right? A radius to a tangent, but that's not happening. All right. They said circle KLMN. So there is a cyclic quad, right? So you're looking for all the theorems that apply to a cyclic quad. Exterior angle equals opposite interior. So that's also 100, for example. Okay. All right. And then chord Kn is produced to S. K2 is 55, blah, blah, blah. Okay, fine. What else do you know about a cyclic quad? Opposite angles are supplementary, or angles on a straight line are supplementary. Right, and they want you to find angle L. That was the first question. And the reason for that is exterior angle of a cyclic quad equals the opposite interior angle. All right. Okay, super. And now we need to find angle O1. Any suggestions? So remember, think of all your theorems, right? There's a center. What theorems do you have with centers? Angle at center twice angle at circumference. So that angle is equal to twice that angle. So this is 160. Reason, angle at center equals twice the angle at the circumference. All right. And then they want angle M1, this angle. Right, any suggestions, anyone? Okay, anybody? Are you guys alive? Why doesn't anyone speak? Oh. All right, so if you look at this quadrilateral, just the normal quadrilateral, the angles add up to 360, and you have 3 of them. All right, so in order to find that one, it's 360 minus the sum of the rest. All right. So in other words, that's not a nice color. 360 minus the sum of the rest. So it's 100 plus 160 plus 55. All right. So this was quite an easy question. Okay, I'm not going to work that out. All right. Just remember to always give your reasons for everything. Okay. All right, next one. Let's move on. All right, so I just want to move this up. It doesn't seem to work when I use my pen. All right, so there's the next one. Question 9. In the diagram, O is the center of the circle. So again, we're looking for all the theorems that involve a center, right? Right, so we know we always need to fill in our radii. Now this is quite difficult to fill in because the radius is there and there. Okay, but then do you agree that O would be the midpoint? Because if this, okay, now that's not very nice to write it like that. Let me use a different color. Right, so this piece equals that piece. So I would do that, just so that it really stands out, that it's the whole piece. All right, and what else do we know about a center? A line from the center to the midpoint of a chord is perpendicular to the chord. Okay, so you've got to know the theorems, right? Which means, of course, if that's 90 and that's 90, they're co-interior, which means this must be parallel to that. Right? Okay, so we're definitely going to have ratio and proportion here, right? Definitely. Okay, then they said, yeah, BOD is the diameter, and the diameter subtends 90 degrees. Remember, if you have a triangle with the diameter as your base, then there is a 90-degree formed at the circumference. Okay. And what else? GO is perpendicular. Okay, we've done that. All right, so now they say, give a reason why angle DAB. DAB equals 90. Why is that 90? Well, you should have already filled it in. So by the time you read it, you go, oh, okay, it's angle in a semicircle. Okay, it's called angle in a semicircle. Whenever you have a diameter that forms a triangle at the circumference, it forms 90 degrees, and the reason you write is angle in a semicircle. Right, then you want to show that AGOB is a cyclic quad. AGOB, this one is cyclic. Well, what do you know about a cyclic quad? The opposite angles are supplementary. Does 90 plus 90 not equal 180? So surely then that must be a cyclic quad. Okay, so it's the reverse. So yes, all you need to say is yes, or give a reason why. You just need to say opposite angles supplementary. Remember, you've already just shown that that is 90. They gave you this as 90, so obviously they are adding up to 180, so they are supplementary. Okay. And then prove that AC is parallel to GO. Well, there we go. If you do your geometry correctly, by the time you read this, most of it will be done. Yes, they are parallel because of the co-interior angles. You can't have co-interior angles that add up to 180 if the lines are not parallel to each other. And then, of course, remember what we said, there must be proportion happening there. Okay. And then prove that angle G1 equals B1. Angle G1. Okay, so this angle, X, call it X, equals that one corresponding because of the parallel lines. And that equals that, angles in the same segment. There's the butterfly. You see that? Okay, there's your butterfly or bow tie. The tips are equal. All right. So you've now proven that G1 equals B1. All right. It's 4 marks. You say angle G1 equals angle A2, corresponding angles. Why? Because OG is parallel to AC. And then you say angle A2 equals angle B1, angles in the same segment. Okay. All right. So if we have the bow tie or the butterfly, those two are always equal to each other, and those two are, if these points are on the circumference of a circle, right? So as long as it's like that, then that equals that, and that equals that. All right? And the reason is angles in the same segment. Angles in same segment. All right. I see lots of chat messages coming through here. Oh, you're talking to each other. Nasir, I see you say teach the theorems from scratch, but I'm afraid I was requested to do similarity, and there's no way I'll get there if I go through all the theorems, I'm afraid. So I'll try and elaborate as much as I can as we go along. Okay. All right, now, as far as this similarity goes, or the ratio and proportion goes, if you have a triangle with another line through it that is parallel to the third side, if you have that scenario, which is what we have here, see it's upside down, then you need to know how to write these ratios. Okay, so for example, you can either write AB over AC, small over big equals small over big, AE over AD, equals small over big, BE over CD. You can write those three equal to each other. Or you can write AB over BC equals AE over ED. And that's all you can write. There isn't a third part to this one. Okay? Because in this one, we're talking about the three sides of the small triangle and the three sides of the big triangle. Whereas here, we're just talking about that over, so that over that. And this is not a side of a triangle from there to there. It's just a piece. So small over piece equals small over piece. Okay, so those are the two things that you would be thinking of in effect. Okay, so that's how it works. And it only works if this is parallel to the other side, which we've now proven, which means that we have the same situation here, right? We have DO over O, what is that letter? F. Okay, so DO over OF, for example. DO over OF equals DG over GA. Or you have DO over DF. I'm going to write it here. DO over DF. Small over big. Small over big equals small over big. DG over DA equals small over big. Okay, so the same as this scenario. OG over FA. OG over FA. All right, so we have one of those two, and there's a good chance that we might have to use it. Now, unfortunately, I have to move this up, which messes up my whole thing. If it is given that FB equals 2/5 R, FB equals 2/5 R, I just want to write it down. FB equals 2/5 R. What do they want you to find? Where R is the radius of the circle. Determine with reasons the ratio of DG over DA. DG over DA. Now look at that. There's a DG over DA there. DG over DA. So it's probably got to do with this one. Okay, if they're trying to find you, they want you to find that. Now these questions are always tough. Okay, it's just tough. Okay, FB is 2/5 of R. Now R is the radius, so this whole thing is R, right? So how would you write that? Because this whole thing is R, that's 2/5 of it, and that's 3/5 R then. Okay, I want to try and use a different color. So this is 2/5 R, and this is, for what it's worth, 3/5 R. And I think that might be important, because if we look at this, dg over dA, which is what they want us to find, it's the same as dO over dF, that. Now, what is dO over dF? dO over dF, dO is r, right? The radius. So it's r over, and dF is r plus 3/5 r. So 1 plus 3/5. 1 and 3/5, that's 8 over 5r, right? Just double check me. 1 plus 3/5, correct. And then the r's will cancel, and you'll have 1 over 8 over 5, which is tipping times 5 over 8. And it's the same as dg over dA. All right. So these are always tough, right? They're not easy questions. All right. But you've certainly got to look for that scenario, okay, of a triangle with a parallel going through it. In fact, when you looked at this, you should have, even though you didn't know that this was parallel, it looks parallel, and you should have gone, I wonder if I'm going to be using that in this, and then know how to write them out. Okay, it's important. Yeah, it's quite difficult, I know, but it's practice. Okay, it's quite fun actually. All right, so that was that one done, and they are difficult in general. Okay, now what happens is you often find that the first few questions will not be too bad. Just trying to find my eraser somewhere. It's like vanished. I don't know why, but my whole pen thing has vanished. My pen's working, but I can't erase for some reason. Why not? Okay, wait, let me stop sharing. If I do that, it sometimes works. That's bizarre. Oh, anyway, it's fine. We'll just start afresh. All right, and we'll start reading through the next one. Okay, question 10. I just want to see if it's also proportion. It probably is. No, not really. So this is a good one for somebody who asked to go through all the theorems, okay? Some practice with this. Oh, now you see, now suddenly that thing has appeared. Weird. In the diagram, PA and PT are tangents to the circle, okay? So this equals this. And immediately when they say that, you know that this angle equals that angle. So just indicate it so that you know that. Okay. Isosceles triangle. When you have a tangent to a circle and you have a radius or a tangent, it's 90, but I don't think there is one. Blah, 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 blah. BR equals AR. BR equals
Excuse me, ma'am.
Yes.
I think the screen is a bit blurry on my side. I really can't see what's written there.
Have you tried to increase your screen size?
Okay, I'm gonna try that now.
Yeah, because I've increased mine. I don't want to increase it anymore because it's difficult to get back to the pictures afterwards once I move it.
Okay.
Is it working?
Yes.
Okay. All right, so now they've also told you that BR equals AR. And I'm going to change color here because it's difficult to indicate that with the same color. So this whole line equals that whole line, which makes this isosceles as well, which means that you know that that is equal to that. So this one's going to be not such a nice one. And they've also told you that angle T3 is equal to x. Okay, now you're going to have to look for as many angles as you possibly can here. All right? Remember when they tell you that you've got a tangent to a circle, you're looking for the tan chord theorem. Okay, so if you look at this triangle, that triangle, there's the tangent to it. The angle between the tangent and the chord, y, is equal to the opposite one. So not along this line. This angle is off this line, opposite that line, opposite the chord. That's why it's called the tan chord theorem. This chord subtends that angle. So those two are equal to each other. And then also you have the bow tie here. Angles in the same segment. So that's also y. You see that? There's the butterfly. The tips are equal to each other. Not so. Right. Okay, and there are other tips, right? There's that one is equal to that one. And there's that one equal to that one, for example. So if you call this P, then that's P. There's a lot going on, actually. And that one equals that one. So K, K. But you do know that these two are equal to each other, right? Just by the way. All right. Okay, what else? We have another tangent here. Right, so if we look at this tangent, and we look for the tan chord theorem, there's the triangle, then this x equals that. So actually the P is an x. So go and change the P to an x. All right, so there's the tangent. There is the triangle. The angle between the tangent and the chord is equal to the angle subtended by the chord. Okay, it's this thing. It's when you have a triangle, all 3 points must be on the circumference, and you have a tangent at the one point. Then this angle equals that angle, and this one equals that one. All right, and you've literally got to know that. You've got to look for the triangle and know that those two are equal and those two are equal. Okay. All right, so here we knew that this one was isosceles, and that's a y and an x, and this is a y and an x. Makes perfect sense, right? Right, okay, so what did they actually ask us to find? Let's go and have a look. It's always a bit tricky moving this thing up. So they said, give a reason why angle T3 equals A2 equals X. Angle T3 equals T2. T3 equals A2. So that's what we proved. We proved that T3 was equal to A2. Right? And how did we prove that? We proved it from the tan chord theorem. All right. Then they said prove that AB is parallel to ST. Prove that AB is parallel to ST. AB parallel to ST. Now, do you see that triangle again with the parallel through it then? Because if they're asking me to prove that parallel, then I'm probably going to use some kind of a proportion. Maybe, okay? All right. So for me to be able to prove that these two are parallel, I need, what kind of angles do I get when I have parallel lines? I have alternate angles. I have corresponding angles. I have co-interior angles that add up to 180. Okay, so somehow I need to show that this is parallel to that. How will I do that? Because for me to do that, I need to prove alternate angles, right? So parallel to parallel, I'd have to prove that those are both A or both Y. And I need to be thinking about why it would be that, right? Now, did we not say that this angle was equal to that angle? But this little piece is X. So surely the other piece must be y, right? Y plus x, y plus x. We knew that they were equal to each other. All right, and therefore we have alternate angles, which means that these two are parallel to each other. Okay, so you've got to think in reverse. You've got to say, okay, well, hang on a minute. There's no way that these can be parallel if I don't have alternate angles. So how am I going to get those two to be the same? And then you start searching. You go, well, that's y. This is not y. How can I make it y? Where's my other y? There. How can I relate this to this? Ah, part of it is x, but this whole thing is the same. So the other part must be y. Its other part, right? All right, and that's how you go about it. Okay, it's quite tricky actually. But you do get the hang of it eventually. And then there as well, that would then be alternate. So this would also be a y. Not so. Alternate angles. All right, and I think we answered what they wanted there. Oh, goodness, why isn't this working now? Really? Come on. Oh. All right, so what else did they ask? They said you must prove that angle T4 equals A1. Well, T4 equals A1. Does T4 equal A1? In other words, and if A1 is a Y, I'm going to try and get this one to be a Y. Right, so I somehow need to try and get this to be a Y. All right, okay. Well, certainly I have, what do I have? I have a cyclic quad, right? And I know that the exterior angle of a cyclic quad, this angle, is equal to that angle. In other words, x plus y. And if that's x, then that must be y, because that is x plus y, and that is x plus y, and part of it is x, so the other part must be y. So now I've proven that this one, F4, is equal to A1. Right, it relies a lot on you preempting. Okay. What else did they ask? They said, prove that RTAP is a cyclic quad. Prove that RTAP. RTAP, that this thing is a cyclic quad. Well, what do we know about a cyclic quad? The answer is there. What do we know about a cyclic quad? We know that the opposite angles are supplementary. Well, there's no line here, so it's not going to be opposite angles. We know that the exterior is equal to the opposite interior, but there's no line there, so that's not going to work. And we know the bow tie, angles in the same segment. There's your butterfly or bow tie. The tips are both Y. They're both equal to each other, which means that this must be cyclic. So you're doing it in reverse. When they say show that it's a cyclic quad, you need to be thinking of all the things that would make it cyclic, right? All the theorems to do with a cyclic quad. And don't forget, a cyclic quad also has angles in the same segment, right? So if you have something like this, and you have lines going across, okay, that equals that. Okay, there's your butterfly. Tips are equal, bottom tips are equal. Then there's that butterfly. That equals that, that equals that. All right. So don't forget about angles in the same segment, because that's enough to prove that it's a cyclic quad. All right. Okay, we kind of digressed a little bit, but on Wednesday, I'll carry on. Okay, we'll carry on and we'll do more similarity. All right. Because I think I've dented the theorems a little bit. They'll obviously come up again, and then we'll go through whatever else, but I'm going to try next time to focus on the actual similarity part, like this next question, for example. All right, you can maybe go and have a look at it on your own. 2017 paper. It might be the February-March one. Double check. Okay. All right, so we'll do this one next time. This will be the hardest one in the paper, okay? The last question is normally the tough one. But having said that, normally it's in parts, and the first couple of parts are okay. It's only really the last part that tends to be really not nice. Okay. All right. I just want to clear here. And just let's read through this, familiarize ourselves, and then we'll try and carry on with it next time. In the diagram, A, B, C, D is a parallelogram. Okay, now if it's a parallelogram, you already know that the opposite sides are parallel and equal. Parallel and equal. And you know that the diagonals bisect each other. So in other words, that equals that. Now, if this whole piece equals that whole piece, and some of it's the same, then surely that must equal that. Okay, so that the whole piece equals the whole piece. And the same here, this whole thing equals that whole thing. Let's just remember that one. And then also remember that you have alternate angles, okay, because of the parallel lines. So x, right? Y, and the same the other way around, because the opposite angles are also equal to each other, and then k. So something like that so far. And what else do they say? TP equals PS, we've used that already. But you see that this should already be standing out somehow, to do with maybe the parallel. We don't know. Right, and what else do we know? We have a circle, so is there anything here that we can fill in? Is there a cyclic quad? I don't see any cyclic quad. This is quite an unusual one. No, there's no cyclic quad because there's no line there. All right, perfect. Okay, so it looks like we filled in most things, right? So once you fill in as much as you can, as quickly as you can, then you read the question. Okay, try and preempt things. They want you to prove that AT equals SC, and it's probably going to cut out the session. Now I can't get it in the exact place. Oh, no. There we go. What was it? AT equals SC. Well, we already did that, right? They want you to prove that AT equals SC. We already did that. All right. I'm just trying to see if this is a parallelogram. We said that that is equal to that as well, right? But this proportion would be the same as that. No, or would it? No, because we don't know if that's parallel, right? Oh, interesting. All right, so what else did they ask? They said prove that triangle PSR, that little one, is similar to PBA. To PBA. PSR. Oh, okay. That's a nice question. Oh, goodness. There we go. Okay, so they want you to prove that this triangle is similar to that. All right. Well, we've already got vertically opposite angles. We already know that let's call it M equals M, vertically opposite. And we already know that equals that, and that equals that. So these, oh, sorry, I'm working in the wrong one. If we look at the circle, we have the butterfly, don't we? So if that's A, that's A. And if that's K, that's K. So these two triangles definitely have the same angles. And if they have the same angles, they are similar. All right, so you're going to have to say vertically opposite, angles in the same segment, angles in the same segment. Therefore, the two triangles are similar. And remember, when you say that two triangles are similar, Name the one however you like. So if it's PSR, if you choose to name it like that, then name the other one with the same angles. PSR is MAK, MAK will be PBA. Because then you're going to do your proportion. PS over PB equals SR over BA equals PR over PA. And you'll find that that is probably going to help you with the rest. Okay, so make sure that if they've asked you to prove similarity and you've proven it, say now you couldn't prove it completely, then still assume that and write out the proportion always, right? But you must make sure that the angles are named in the right order of their sizes. You write out the proportion, and usually you will need it for the rest, okay? All right, so it is further given that PR over PA, do you see that that's on the far right in that proportion that I wrote out? PR over PA equals TR over AD. TR over AD. Okay, so now this is where it starts getting terrible. TR over AD. TR over AD. Now that's interesting, isn't it? Because it would be small over big, wouldn't it? In this scenario. But we don't know if these two lines are parallel, do we? And they're asking you, they're saying, is TR over AD, you must prove equal to PR over PA. PR over PA. Okay, so this one's going to take a lot longer to do. All right. Okay, so your sorry, it's definitely going to cut out any second, so I won't start that, but we'll carry on with this one next week. All right, no, sorry, not next week, on Wednesday. We'll carry on with this one. It's quite a nice one, okay, and it's involves quite a lot of things. But just to give you an idea, TR over AD, it looks like small over big. So maybe there's something we can prove here. I don't know, but I think there's something we can prove here. Okay. All right. Okay. All right. So we'll carry on next time. And I think we'll probably we should spend a few lessons on similarity because it's really tricky. And then I will also elaborate as I go along on the theorem. So the same as I did this evening. We'll elaborate as we go along rather than do them like from scratch because that's grade 11 work. So, okay, cool. Perfect. Awesome, guys. Thank you very much. I'll see you on Wednesday. Bye.
Thank you.
Pleasure.